So we're going to talk about proving the correctness of NFAs. So previously we had seen how we can prove the correctness of a DFA. And we've seen some techniques there. Namely, we've seen the concept of state invariants. We're going to use the same idea here. And the exact same game plan. It's just now instead we're using a different computational definition. So our extended transition function is a little different. So that means that the way we use it will differ from when we did it and try to prove claims with the DFA. In a DFA, we just tried to exhaust all possibilities over some so-called state invariants, and then we just tried them all, unless we wanted to be a bit more clever about it, which is okay. But well, certainly you could do this. It can be a little time-consuming, but it's straightforward. And how would you combine it with induction? So previously we talked about a DFA and how we could prove correctness there. I just want to summarize how the game plan would change a little bit here with NFAs. So we need to ensure that for every input, so for every input W, in the language of our NFA M, it has to be that W's in this language, as we defined, remember this means that W is accepted by the NFA. If and only if, I'll abbreviate if and only if with IFF, the W is in the language we want M to recognize. That's kind of the overall game plan. So this is our game plan. so that is, if I call this language L, if I call this L, that is, a W is in L if and only if W is in L of M. Remember, L of M is the language of the machine. This is just the desired language I would like to prove. They're not the same thing. Well, the goal is to prove that they are the same. But the thing is, we may not necessarily have that. In that case, you would have an incorrect NFA. So we're going to be adopting a similar framework to before. We're going to be trying to use state invariants again. But as I stressed in that lesson when we were talking about DFAs, you don't have to use state invariants. If your DFA has a very specialized structure, just like an NFA may have a very specialized structure, it may require just proving maybe one invariant as opposed to using a state invariance over all of the states. You might not need over all of the states. You just need maybe just one or two potentially, or just, it depends heavily on the NFA or DFA in question. So similar to with DFAs, suppose we want to prove NFA M and language L satisfy L of M is equal to L. Remember, L is the language, L of M is the language of that machine over there. In this framework, you would employ an argument just like this one. Employ the following argument. So the first thing we do is we identify state invariants. So this would be how you would prove the claim, or at least the main part of the claim. So identify state invariants. So just be clear what I mean by this. For every state Q in the state of the set of Q's, we're going to determine some language LQ such that when M transitions into state Q upon reading string W, W is in LQ. Specifically, what I'm saying is that W is in LQ if and only if the state Q is in the extended transition function. It's in the set of states resulting from computing the extended transition function on Q0 W. So upon computing the string on W, if it's in, sorry, this should be Q, not Q0. It should be Q. When I actually no, fine. Q is, yeah, it is Q0. It's Q0. My apologies. Yeah, what matters is that Q is in the set of states upon processing W. So this if and only if has to exist. So you do this for each one of the states. That's the first step. So that's the hardest, I would argue that's probably the hardest step, is identifying those. The rest of it is a little bit more of the busy work, okay? But you have to check, okay? Is now you got to actually prove the state invariance. So the way you design your NFA will play a big role on how you identify the state invariance. So so a part of this process of proving the correctness of the NFA may play a role in how you design the NFA too. You might want to design the NFA so it's easy to prove that the NFA is correct, and then work your way from there. So prove the state invariance. So using induction. So you're going to perform mathematical induction on the length of the string. So on the length of W. Prove for all input strings W. For all input strings W. And every state Q in Q, what you want to do is you want to prove that Q is in delta hat, the resulting states of delta hat. Remember, there's a hat here. It's not just transition. It's the extended transition function of Q0W. So just upon processing the string starting at Q0 on string W, if and only if W is in LQ, as I previously stated. But you'll prove this using mathematical induction. So you go through each one of the states and you just simply argue that that is in fact the case. So depending on how complicated the transition function is, it may change how you might go about it. I'm going to show you in my example a variety of different ways of going about it. But I must stress that if you think carefully enough, there might be other ways of going about it, as long as you understand how to prove an if and only if claim. So the point is we work with some logically equivalent statements, or we might try to prove it using two-directional proofs. So I might try to prove it given this, that this, if given that, then prove this. That's another way you might want to work with this if a state invariance is a little bit more complicated. And lastly, you just use the definition of L of M. Remember, the definition says that whatever the result is from Q0 upon reading string W, intersect the set of final states. As long as that isn't empty, it accepts, right? So all you do is you look at the set of final states, and you look at all those languages, the ones like these LQs, just look at the ones for the final states. Take those together, and boom, there you go. So prove that the desired language L is actually going to be equal to the union over all of the final states for L of Q. And that's the way you could use state invariants in the context of NFAs. But I must warn you, one detail I must warn you about is that when you're considering state invariants here, remember we have to keep in mind the definition of computing for an NFA. Remember, the game in town with the DFA is that I know given a state, a symbol, I know which state it's going to go to. However, here, if I go to some state, I may have gotten there through several other means. So that's what's going to make the proof of correctness with an NFA be quite a bit different sometimes than with a DFA. In a DFA, it's quite natural to exhaust all possibilities. But with an NFA, it may be the case that sometimes it may be a little tricky to do that. So you have to be very careful when you're arguing claims about the state invariants. So to carry out our example here, I'm going to use a previous example we had when we were designing NFAs. So I'm going to show you that one of the NFAs we presented is in fact correct. And we're going to do that using mathematical induction and the technique of state invariants. So we're going to use state invariants. We're going to cook up some state invariants. We're going to prove those state invariants. Then observe that one of them actually tells us exactly which language the NFA recognizes. And then we're done. I make it sound so easy, don't I? But the thing is, once you understand the main idea of this technique, this argument, it's not too scary. It's just that you need to think very carefully about it. Not everything in this world's easy to just cook up out of the blue. You have to sometimes just sit there and stare at things for a while and really play around with the ideas you have in front of you, which is always something that somebody like myself does when I do research. It's not unusual to sit in front of a board for hours on end trying to figure out something. That's something that is perfectly fine to happen. And when you're first studying theory of computation, same thing happens, okay? So let's consider this example. So I presented this NFA. I was about to say DFA, but let's consider this NFA. Recall, this is the one that I gave you that detects if the string ends with 1, then a 0. So remember, the claim here was that this NFA, it detects binary strings which end with 1, then 0. So we're going to prove that it is indeed the case. But what I want you to really think about is state invariants. So let's think about some state invariants for this. So let's think about this. What can we say about Q0, Q1, and Q2? If I have a string, so upon reading a string W, if I end up in Q1, or end up in Q2, or end up in Q0, what can I say about the string? Now, one thing that's going to make this feel a little different than with the DFAs is that here, it may be the case that not every string will map up to exactly one of the cases. That is a feature of non-determinism that we would like to exploit in our design sometimes. So, what can I say about Q0? I alluded to this when we were designing this NFA. Is notice that no matter if you read a 0 or a 1, it always, if you look at the states of the NFA, Q0 is always in there. So we can carefully characterize this. So Q0 is in delta hat Q0W if and only if what? W is a binary string, right? But you can even go even further and literally just say that Q0 is in here at all stages of the execution. But I'll just state it like this. So if W is a binary string, it has to be that Q0 is in here. that is most certainly a fine state invariant. So with NFAs, if you have it where you have this approach where we try to keep making guesses, producing more guesses like this is not something very surprising. How about Q1? What can I say about strings W? So if I give you a string and you end up in Q1, what can I say about that binary string? What can I say about it? Well, let's think about it. How did I get to Q1? There's observe, and this is something that will come up in our proof, is observe that the only transition into Q1, or even to remaining Q1, is from Q0, and it's over this symbol. What's the symbol? 1. It's just 1. So that means that the string has to end with a 1. So Q1 is in delta hat Q0W if and only if W ends with a 1, or ends with 1. So if it ends with a 1, the claim is that it will be one of the set of states. Finally, Q2. Well, this should match up if we are correct. And Q2 is the final state. We sort of gave away what Q2 should be then. W has to end with 1, 0. So W ends with 1, 0. These seem like perfectly reasonable state invariants, right? If we can establish these state invariants, notice that Q2 is the final state. Hence, that's all we need to prove the correctness of the NFA. However, as I explained previously when we were talking about state invariants, sometimes it's very difficult to know because all we have at our disposal are the set of states that we currently are in. I don't know how it got into that state up to that point, except for it may have been for some other reason. It may have been because, hey, look, I was in Q1, I got to Q2. Why did I get to Q2? I read the 0 here, right? It's pretty straightforward. However, it could be the case that I read a 1, but I was in Q0, but I could have stayed in Q0, but I could be in Q1 as well. So a very similar thing happens as well with NFAs. So it's a good idea we carefully go through and see what happens in each case, on each transition, namely. So this is what we're going to prove. This is the primary claim. Once we have that, we just look at this row right here, and that will give us the correctness based on using our argument for state invariance. So here's our lemma. So we're going to prove this lemma. And once we have that, we just have that one piece of the argument to get the correctness. So given NFA M, but I'll refer to this just in our proof as M end, just to keep it simple for us. NFA M end and W, which is some binary string. It has to be, this is true for M. So upon processing string W, if you're in Q0, it has to satisfy this. Q1 satisfies this. Q2 satisfies that. That's the claim. We're going to prove this using mathematical induction. So please, if ever we need to go over here, just keep in mind this transition diagram. So to prove the claim, we use mathematical induction. mathematical induction on the length of the string W. So what's the first thing we do in an induction proof? The base step, right? So we're going to start off with the length of the string is 0. Since the length of the string is 0, there's only one string with length 0, right? The empty string. So let's just see what happens when we're given the empty string. We'll use the definition, the basis of computing's definition on an NFA. I know it sounds a little bit weird, but go with it, okay? So let's consider the definition of computation for an NFA when we're given an empty string. Well, we stay in the same state, right? So let's see what happens. So in this case, W is equal to the empty string, and by definition, it has to be that delta hat Q0 W is equal to the set that contains only Q0. So remember that the string W, it's a binary string, right? It just has no symbols. String W is, in fact, it belongs to the set of all binary strings, right? So what can we say? Well, it's in Q0 is one of the states that you get, so, and it is a binary string, so we're okay there, right? So the first invariant, I'm just going to number these invariants. So the first invariant, so 1 holds. So 1 holds. How about 2 and 3? Because remember, all 3 of these have to hold. And remember, it's an if and only if claim. So logically speaking, if Q1 isn't in here, then it has to be that W does not have this property, right? Likewise here. If Q2 is not in here, then that means that W doesn't end with a 1, 0. So, well, let's see. The empty string most certainly doesn't end with a 1, right? So we're okay here. And it doesn't end with 1, 0, so we're okay here too, right? So let's just say that. As epsilon, the empty string, does not end with 1 or 0, and the set of states does not include Q1 or Q2. I'll just say 2 and 3 hold. Hence, the statement is true. Statement referring to the lemma. The statement is true for all strings of length 0. So it's true when W has length 0. So now we've completed the base step. Now we got to get to the induction step. Now, if you aren't just like, okay, I want to check some more cases, you're welcome to go check when the length is 1 and the length is 2, but you'll find that my argument here works regardless. So you might be compelled to do something like that, and keep in mind, for some NFAs that might make things easier, or it depends on your argument. But notice that the only strings that get accepted here are going to have length 2 or more, right? So that might be helpful depending on what kind of argument you're trying to impose here. But I'm trying to use a little bit of a broader argument here that requires me to just check things a little bit more carefully by using a stronger induction hypothesis. So just please keep that in mind. So just don't think that you just have to prove this case. You could go up higher if needed for your induction hypothesis, okay? Well, now let's consider the induction step. We're going to fix going to fix some n greater or equal to 0, right? Because we proved it up to and including 0, right? So I'm going to go up one notch. Let the length of the string w equal n plus 1, assuming, so this is really important, this is the induction hypothesis, assuming the statement for all strings of length n holds. So that's the induction hypothesis. So we're going to show how to prove the claim for all strings of length n plus 1 that follows from the induction hypothesis. So let's check this out. So consider w, and remember this is an arbitrary string, w equal to xa. So we're going to use a very similar setup to that we did with the DFAs. So I'm going to have all of the symbols just before the last symbol. The last symbol is a. What can you say about x, by the way? What's the length of string x? What's the length of the string? If this is whole thing's length is n plus 1, the length of x is what? It's n, right? So we're going to use that fact to help us here. So, where a is the final symbol in W, presuming that x is everything but the last symbol. Now we prove that the statement, the lemma, that the statement also follows. So remember, we need to use the induction hypothesis here. That's a key part of the induction step. We have to show, when I give you n, I'm going to show you where it follows that if n was true for all strings of length n, it has to follow for all strings of length n plus 1. That the statement also follows for string w. Now, as I alluded to, what's the first thing you might try doing here? We've got the setup. What should we do? Any suggestions? Any suggestions at all? Well, I alluded to this. Look over there. What can I say about this? So remember, w is equal to xa. This is one symbol. How many symbols are here? N. There's n symbols there. So x has length n. So I'm going to use the induction hypothesis. I'm going to apply it to x. Then all I have to do is put the cherry on top by seeing what happens when I deal with a. So string x has length n. So by the induction hypothesis or inductive hypothesis, we could say the following. First, that Q0 is in delta hat Q0 x. So upon processing x, starting at Q0 with this NFA, it's in Q0 if and only if x is a binary string. Unsurprising, I know. It's amazing. 2, Q1 is in delta hat Q0x. So upon processing x, it's in Q. Q1 is one of the states if and only if x ends with a 1. And lastly, state Q2 is among the set of states upon reading x if and only if x ends with 1, 0. So now we have this with x. We're going to try doing something similar to what we did with our DFAs. So I'm getting really excited. I'm getting really excited. So let's get into this goody juice, okay? I'm going to keep the NFA on the board, but I need you to remember these invariants because we're going to use them. Because we're going to keep this NFA up on the board because it'll be helpful for when we're proving the claims. So just remember the lemma. The lemma is going to be that, except it's string W. Any W. So once we get the induction step in place, we can then use the principle of mathematical induction and complete the proof. So now that we have this, we prove each state invariant holds for W separately. Now, one telltale sign you're working with something slightly different is remember that when I did this with the DFA, the last symbol, it either was usually a 0 or a 1 if we're working with a binary alphabet. So I had only like 2 choices. So say if it was in state Q0, Q1, or Q2, I would have at most 6 cases where I would check what happens when it processes X and it's in a state, and then I look at what A is. I would do that for each one. There's a bit of an issue when doing this with an NFA, is as previously described, it could be the case that there's a reason how X contained a certain state. But remember, they may contain other states too. Likewise, there has to be a reason why that state was included as part of the set of states. So instead of working with X, where I break down the cases on X, I'm going to break the cases on W. So I'm going to directly have it where I'm going to have 3 main cases, one for each of the state invariants where I consider all strings of length n+1, and I'm going to use in each case those guys over there. But I need to the best way I can describe this to you is I'm going to reverse engineer how X got there. And I'm going to use, I need to carefully ensure I can use these cases that I have here to ensure that I can derive what happened up to that point. So watch this carefully. It's almost like reverse engineering how I got there. And use properties about the NFA to tell me how I can only get there by a certain means. So let's start with proving the first invariant. So let's consider state invariant for Q0. So this one's going to be not as interesting. String X was already a binary string, right? I didn't say that state invariants have to be these very ingenious things, okay? So, and it also has to be the case that W is also a binary string, right? There's nothing impressive about this statement because A is either 0 or 1, right? So if X is already a binary string, then W also has to be. That establishes one side of the invariant, right? So since I already know that X is already a binary string, then I can say what's going on at Q0, right? Because X, by the first invariant, would be here, right? Because it's a binary string, regardless of what W is. So state Q0 is in delta hat Q0X. So upon processing X by the first invariant, And I must stress this is on X. So I'm applying what we have over there. So state Q0 is in delta Q0A. So I'm applying the transition function on Q0 given A. And 1, so the first invariant remains satisfied for W. So please note that the way I was able to invoke this right here was because I knew X was a binary string, right? And because of that, I could say, okay, well, look, I could just use the first one over there on X, and then I just look at the transition function. Okay, Q0 on A, regardless if it's 0 or 1, Q0 is in this set. So that means it's still in, so Q0 is still in the set when I apply it on W. So that proves the first invariant for all strings of length n+1 for the induction step. Remember, we're just trying to show that going from n to n+1, we're trying to use the induction hypothesis from all strings of length n to get to the next symbol. So that was one of the easy cases. So let's consider the state invariant for Q1. So the state invariant for Q1, remember, that means that upon reading string W, I have to have it where the string ends with a 1. So string W ends with a 1. It means it's right here for one of the states. So it means Q1 is in the set of active states upon reading W. But how do I get to Q1? How do I get to Q1? How do I get here? Let me put my Explorer hat on for my very unexciting adventure, okay? Why do I say that? The only way I could get to Q1 is from Q0, right? Because that's the only transition into Q1 is from Q0, right? So that's how I could get to Q1. So it tells you something really special about X. But here's the kicker. Here's the kicker. We already have an invariant that tells us any binary string is in Q0 is one of the active. Remember, X is a binary string, right? Sorry, I'm getting really excited. Somebody's got to count how many times I said that. But when we consider, remember, Q0 is among the set of states that are active at all stages, right? So I can use that fact. So to prove the second invariant, I'm going to use the first invariant from our claim, right? So specifically on X. So by the first invariant, so I get for free from the first, so I get from number 1 over there on X. By the first invariant on X, upon reading X, Q0 is in the set of states upon reading X. So please note that the way I got this was because X has to be a binary string. That's how I got this. So that's how I'm using that over there. I'm using number 1 over there. Now, there's only 2 possibilities for A, so I'm going to do something akin to what I did for when I was proving this kind of claim on a DFA, as I'm going to exhaust all possibilities of A. We consider two possibilities for A. A is equal to 0 or A is equal to 1. Those are the only two that can happen with A. So we're going to have two cases. Let's head over here. So remember, we know that Q0 is one of the set of, it's a state that's currently among the set of states while I'm processing X. So now what we need to do is we need to look at the cases when A is equal to 0 and A is equal to 1 separately. See what happens. Does Q1 belong to the set of states in the appropriate case, or does it not? But the trick is, because I got my Explorer hat on, is remember, there's only certain states that you can get into Q1 from. We're going to use this fact. So we're going to call this one case A. So this is going to be A is equal to 1. Well, what can we say about the string in this case? Well, W has to end with a 1, right? So in this case, it most certainly should be in Q1 when we're done reading W. In this case, W ends with 1. Well, now that we know this as a matter of fact about A, well, let's just apply the transition function on Q0 reading 1. Well, Q0 reading a 0 is, actually not reading a 0, reading a 1. We want to read a 1. Well, what is this? This is Q0, Q1, right? Right, it either is still in Q0 or it has Q1, okay? So, but the thing is, it has Q1 in it, which contains Q1 as expected for 2. But now here, it should not be the case that the state invariant is actually going to be true in the positive sense, right? It should be now that it must not be in state Q1 because it doesn't end with a 1 anymore, right? So notice W equals X0 does not end with 1. Now, this is where, so now we know on one side of this thing that yes, it doesn't end with a 1, right? So think of my Explorer cap. What can we say about this situation? Observe that the only transition upon reading X to state Q1 on A is from Q0, right? And what can we say about the transition on 0? Well, it stays in Q0. And delta Q0 on what? 0, right? Not X, on 0, because we want to know where we're going, right? Like I said, we're trying to reverse engineer where we came from. We're using a specialized structure of the NFA to figure out where we could have possibly come from. So Q0 on 0 is, in fact, just going to only contain the state Q0, which does not contain Q1. Hence 2 has to hold, right? Hence 2 holds for W. So remember, the goal in this case was to establish, notice it doesn't end with a 1, so it has to be the case that Q1 is not among the set of states. Here we established it's not a part of the set of states. It's not Q1. Q1 isn't. And the way we knew this is because the only transition upon reading X to state Q1 had to have come from Q0. Because remember, I got my Explorer cap on. It means I know where I'm going. I know where I'm going. It means that I can't be coming from Q2. And I can't be in Q1, right? It's only Q0. So that leaves us with one last case. And this one's a little bit more complicated. I encourage you to find other ways to prove this claim. I'm going to, based on what I alluded to earlier, I'm going to use an if and only if two-directional proof. So let's consider the following. So what we're going to do is we're going to prove this in each direction. So I encourage you to think about trying to prove this claim using an approach similar to the second invariant here. So give that a try. This isn't the only way to go about it, but you'll find that when you start dealing with situations where it's a little bit trickier to apply our observations about X based on the induction hypothesis, it becomes a little tricky. Sometimes it's best to kind of break it into the two directions of the proof because it's an if and only if claim. But you're going to notice very quickly that I'm going to use, for proving this state invariant on our induction step, I'm going to use the second case here. So on X specifically. So we need X on X. There's going to be two directions to the proof. Remember that I want to show the following, right? I'm just going to put it off to the side here so you remember. Remember, it's Q2 is in delta hat Q0W if and only if it ends with what? It ends with, I believe we want it to end with what? Ends with 1, 0, right? So to prove a two-directional proof here, I can start with this and work to get this, and then I can work from here to get this. So we're going to start by going this direction. So we're going to prove this direction of the proof first. So when Q2 is in delta hat Q0W, notice that again, this is going to be using my my little hat, right? I got my Explorer hat on. What can I say about if Q2 is in this set upon processing W? Where had to have come from? Well, look, there's no loops or anything here. It had to come from Q1, so processing X, I had to have had it where the active state was containing, sorry, the active set of states at that time upon reading X had to have included Q1. That's the only way I could have gotten to Q2 upon reading a 0, for example. Either way, it's the only way I could get to Q2. Like I said, we're trying to reverse engineer where we came from. So notice that the only transition, this is transition, sort of melted in the microwave. transition incoming to Q2 upon reading X is from Q1. So what can we say about Q1? Q1 is in delta hat Q0X. So it means that Q1 had to have been a part of the set of states upon reading X. So now that I know this, I have an idea what the form might look like, okay? So as Q1 is in delta hat Q0X by 2 on X, X ends with 1, right? That's what it says. That's what we got from the induction hypothesis. So we know it ends with a 1. That's what X ends with. Now, I pointed that diagram over there to help us. What's the only way I can get from Q1 to Q2? It's over a 0, right? Okay. So let's put this in words. The only transition from Q1 to Q2 is on 0, right? And Q2 is in delta hat Q0W. So to have this property means that it has to use this transition, right? But it's only on a 0. But what does that mean? Thus W ends with 1, 0. Right? So I started here. So if this, then that, right? So that direction of the proof is finished. Let's prove the other direction. So now I'm going to imagine I have a string that ends with 1, 0. I'm going to show you that Q2 belongs to the set of states upon reading string W. So consider string W when it ends with 1, 0. As W equals XA, both X ends with 1, and it has to, what else do we know? And A has to be 0. That's the form of the string, right? So notice the minute you have this, that it ends with 1, most of the work is done, right? We use the second invariant on X. As X ends with 1 by 2 on X, Q1 is in the set of states upon processing string X. Now, we just point our finger at the transition function, then we're done. Since delta, so I'm just going to use the transition function, since my delta is just sort of turning into music notes. Since delta Q1 on 0 is going to be the set with Q2 in it, by definition, so by pointing at the definition of the extended transition function, we can say that Q2 is in delta hat Q0 upon reading W. So that proves both directions of the third invariant, establishing the third invariant holding for all strings of length n plus 1. Hence, the statement follows. Hence, the statement follows for all strings of length n plus 1, completing the induction step. Now, let's just invoke the principle of mathematical induction, and then we're done, right? Then we've established all three invariants, because the principle of mathematical induction now will state that all these things that we established, they'll hold for all n greater or equal to 0. Therefore, by the principle of mathematical induction, the statement holds or is satisfied for all strings of length at least 0. And that completes the proof. Piece of cake, right? So remember, the whole idea here was identifying the state invariants. Then what we did was we went through and proved each of the state invariants for the induction step upon completing the earlier parts of our induction proof. Since we didn't really have a good idea of where we could come from in each one, I broke it up by the state invariants themselves and reverse engineered where X would have been, so that I can use properties of X and infer properties of X. So we're not quite done yet, though. We have one more thing that we really have to do. We're not quite done yet. We haven't really proven the correctness of the NFA quite yet. We haven't finished the proof for proving the correctness of M-end. Here's an argument that we're going to use now, the last step in our proof. So keep in mind, this proves the lemma. This is now a new part of this. If you need this to be in your proof of proving the correctness, I'm going to give you the argument first, then I'll state the theorem. We observe that the final state of M-end is Q2. Then it follows that any string W accepted by M-end must follow that Q2 is among the set of states upon processing string W. That's what this means, remember. Therefore, what can we say? By our lemma, any string accepted by M-end, I was about to say W, by M-end, if and only if W ends with 1, 0. Thus, now we can state our claim, the result. So here's the theorem. Is that the language of M-end is equal to the set of all binary strings such that W ends with 1, 0. Thus, we have established the correctness of this NFA.